we all know that one of the very important use of textile is in clothing, and probably the textile started with the very idea that we need to clothe the human beings in order to protect themselves from rain, wind, heat and many others natural calamities. So, therefore, it is very important for us to know what are the basics science behind the clothing. So, when we discuss the use of textile in clothing, the first thing that should be clear to us is the heat exchange between human body and surroundings or environment, we can say. So, this is the very first step, and you will see that the human body generates heat as well as moisture. So, the clothing has to tackle both heat that the body generates, it is the metabolic heat, and the moisture that the body also generates continuously. So, these two are very important aspect that we need to tackle. Now, what are the different sources of heat generation? We should know that the first thing is basal metabolic rate of all body cells, and therefore, it is called metabolic heat that the body is continuously generating. A dead man cannot generate heat. So, therefore, a dead man is always very, very cold. Otherwise, since birth we are always generating heat, and this is the manifestation that we are basically alive. The other source of heat is produced by muscular activity. That is, if we do some activity, if we walk, if we run, if we do some physical work, then also we generate some additional heat. The other one is metabolism caused by other biochemical cell activity as cell temperatures. So, these are the basic sources of heat. Against this, we will see that what are different activities and the kind of heat the body generates. Like if we sleep, then the heat generated by the body is around 70 watt. When resting, a person generates it around 90 watt. So, different activities are listed here: walking, cycling, hard physical work, and you see the corresponding heat that the body is going to generate. Now, this heat needs to be dissipated. If it is not, then the heat is going to accumulate, the temperature of the skin is going to rise, and you are going to feel very, very uncomfortable. Let us know few things related to the body temperature. The core body temperature is around 37 degrees centigrade. The skin temperature is 33 to 34.5 degrees centigrade, and as long as the skin temperature lies in this range, we feel comfortable. The human beings will feel comfortable. The core body temperature, when it is 35 degrees centigrade, it leads to hypothermic reactions. That is, temperature has fallen by 2 degree. This is something is not good for the human. When the skin temperature is 34 degrees centigrade, you see just temperature difference by 1 degree, the blood flow to skin actually start reducing. That is what is going to happen. See, blood is continuously flowing from heart to the entire body, and this heated blood is actually actually transporting the heat throughout the body. The other thing is the skin temperature when it is 15 degrees centigrade, it falls by so much, then cold pain begins, that we will start feeling pain. We will feel our fingers, or suppose the finger temperature has gone down 15 degrees centigrade, or toe temperature has gone down to 15 degrees centigrade, then the cold pain will begin and there will be numbness also. These problems will be there. At 7 degrees centigrade, if it comes down, both motor and sensory nerves are blocked, resulting paralysis. Therefore, skin temperature should not be allowed to fall below 15 degrees centigrade for useful work. So, under no circumstances, especially in cold environment when a person is going to work, it has to be ensured that the skin temperature should not fall below 15 degrees centigrade and not below 8 degrees centigrade for maintenance of sensation. So, these are the values which are very critical. So, we should be aware of that what is the consequence of body temperature or skin temperature falling. Now, mean weighted skin temperature should be greater than 28 degrees centigrade. If we measure the skin temperature is not exactly same throughout our body. At different places this temperature may be different to some extent. So, they are not exactly constant, but mean weighted skin temperature should be always greater than 28 degrees centigrade, and local skin temperature at any site should be greater than 18 degrees centigrade, so that we do not feel the cold pain. So, these are some of the temperature threshold which is important while designing clothes, especially for cold climate or cold environment. Next, as we said that the body also generates some moisture. Now, the insensible perspiration that is generated by the human body is around 15 to 25 gram per hour in most of the condition. Insensible perspiration means that we are perspirating, but we do not feel the wetness because of this. All of us are continuously generating some moisture from the skin, which is escaping into the atmosphere, but we do not feel that. It is therefore called insensible perspiration. The insensible perspiration, as a function of time, the rate of perspiration generation has been shown by this scientist, that this is dm by dt is 6.0 plus 1.75 pH minus Pa, where pH is partial water vapor pressure near the skin in kilopascal, and Pa is the partial water vapor pressure in the environment surrounding the body, also in kilopascal. So, that means the rate of perspiration generation depends upon the difference in vapor pressure near the skin and vapor pressure in the atmosphere. So, more the difference, more insensible perspirations will be generated. The the next thing is that the sensible perspiration that we generate that is a perspiration that you really feel, that means it is not vapor, it is actually liquid sweat. So, sensible perspiration is basically liquid sweat. Now, there are certain activity and the kind of sensible perspiration that we generate is also stated here. So, what you see here, like a activity like golf, playing golf will mean 850 gram will be generated per square meter of the body in 24 hours. So much of sweat will be generated. Similarly, for hiking, tennis, baseball, climbing, different activities, the kind of sensible perspiration that we are going to generate are listed here. So, that gives you an idea that how much sweat can be generated per unit time. We can change the value from let us say 24 hours, so we can bring it down to per minute also or per second also, and then we can decide what sort of sweat we have to manage if we want to design certain clothing where sweat management becomes one of the very important issue. Like most of the sports clothing, the sports are such that people will always generate some sweat, and therefore, the clothing that has to be used for such kind of sports activity should be such that it should be able to tackle the sweat that we are generating. The heat loss, because of when the water, liquid sweat or liquid, let us say water is vaporized. So, there is a phase change from liquid to vapor state. The amount of heat that it needs for transforming liquid into vapor is 539 calorie, that is at boiling point. But near the skin temperature, it will need 580 calorie per gram at normal skin temperature. So, normal skin temperature, when 1 gram of liquid sweat is evaporated, it will take away 580 calorie of heat from the body. So, sweat in a way has a cooling power, but sweat also has a negative aspect, that is the sensation is very irritable in nature. So, we never like sweat rolling down from our faces, and we are all experienced sweating, and we know that when the sweat accumulates on the skin, the sensation is is not very soothing, and therefore, what we do? We try to wipe out the sweat first using a towel, and then we go under maybe under a fan or somewhere where there is some wind blowing, so that the whatever sweat is still left on the skin, it starts evaporating, and as it evaporates, it takes away the body heat. The net result is that the skin temperature will start going down, and you will start feeling comfortable. Now, heat exchange between human skin and ambient environment. So, mode of heat exchange, here in this slide we are showing what are the different ways the heat can escape from human body to the environment, or in some situation the body may receive heat from the environment also. If the temperature outside or the environment is more than the skin temperature, then there is a heat flow from the environment to the human body. Or the other way is when the outside temperature or environmental temperature is less than the skin temperature, then the heat will flow from the body to the environment. And what are the modes of heat exchange? Conduction, convection, radiation, evaporation, because sweat might evaporate, and that is also through respiration. So, human body is exchanging heat to the environment by 5 different modes. Heat transfer through and above skin. This diagram gives you some idea about the heat that is moving out from the body. Part of it is passing through the skin and some of it is above the skin. So, convection, radiation and conduction in these 3 modes 75% of the body heat will escape. So, body heat is there in the core part of the body, it will get transmitted through the flesh and bones and will reach the skin, and then from the skin it will escape into the surroundings. And convection, radiation, conduction, all 3 modes could be present, and through these 75% of the body heat will escape. Around 25% is through evaporation, that is through perspiration, that is one is evaporation of the sweat or could be the evaporation of the vapor moisture that the body is generating continuously. Something is lost through respiration, but that quantity is very low, it will be less than 1%. So, it is not, we have not given the value here, but that will be very low. So, major part of heat will escape through convection, radiation and conduction from the human body to the environment, around 25% through evaporation. That is a general idea. So, evaporation through sweat glands as shown here. Next we go to the next slide, conduction heat transfer. See, conduction heat transfer, this equation most of you have studied in your basic physics. So, conduction heat transfers K is H k into T S k minus T A. So, what is small h k is convective heat transfer coefficient, T S k is the mean skin temperature and T A is the air temperature. So, this is a very simple equation which can be used to find out how much heat will be transferred to the environment through conduction. Now, conduction heat loss through contact with solid object from skin is rather limited due to rapid reduction in temperature difference. So, you must know that this mode of heat exchange is very limited in the case of human. If the heated air is moved away, then the heat transfer can continue. So, if you have a mechanism by which the heat air which is next to the skin, as it is receiving heat from the skin, its temperature is rising, and therefore, the temperature differential between the skin and the air layer which is in close contact with the skin, that temperature difference will be gradually less and less. So, heat transfer also will be slowing down. But if the heated air is moved away by some means because of the movement of the body or because of the air is moving, in that case heat transfer will continue. So, loss of heat due to conduction to the surrounding air is about 15%. If we say how much heat is lost through conduction process, because the body is in contact with the air, around 15% heat will be lost by this mechanism. Convection heat transfer. Now, air close to the skin warm up. So, the air which is very close to the skin, that air is going to get warm up and it will start rising, because it will become less dense. We all know that the air temperature rises, it becomes lighter and lighter, because its density becomes less and less. That is why the warm air moves up and the cold air moves down. We all know that in basic physics, you must have been told this. So, in the case of convective heat transfer, because the air close to the human skin is getting warmer, so it will rise, and therefore, a air current will automatically start getting generated. And if there is additional wind, the process will be faster. Now, convection heat transfer, C is following this formula, C equal to H c T s k minus T a. What is H c? Is the convective heat transfer coefficient. It depends upon wind. For nude surface, usually 3 to 4 watt per meter square degree centigrade in calm air. So, you must know this value is basically this much, 3 to 4 watt per meter square, and T s k and T a are the skin temperature and the air temperature. The other mode of heat exchange is radiation heat transfer, and that is R is equal to H r T s k minus T r. H r is the radiative heat transfer coefficient and T r is the mean radiant temperature. It is not the air temperature, but it is the mean radiant temperature. What does it mean? We will learn in some other slide what is mean radiant temperature. Now, this is important. What is important here is almost 60% of the total heat is lost through this mode, radiation mode. So, convection and conduction modes are not that efficient as the radiation mode of heat transfer is. So, 60% of the body heat is actually moving out because of radiation, and the transmission is dependent on temperature difference between the heat emitter and the heat absorber. That in this case, the human body is the heat emitter and heat absorber is the surrounding air. The infrared radiation transfers only few millimeters into the fabric, as it is either scattered or absorbed by the fibers. So, when you have a clothing layer, there are millions of fibers in the clothing. So, infrared heat radiation transfers only few millimeters into the fabric, and it is scattered or absorbed by the fiber. These fibers in turn will emit radiation, which will go to the next fiber. So, you can imagine a fabric, whatever is the thickness of it, still contains large number of fibers in the cross section of the yarn. So, compare the fiber dimension which is in micron with the dimension or thickness dimension of the fabric. So, obviously, a fabric will consist large number of fibers along its thickness also, and the heat will move through radiation from one fiber to the next fiber, from that fiber to the next layer fibers, like that it will move until it will reach the outer surface. That is how it moves, and radiative heat transfer is indirect and depends upon absorption and emission property of the fiber. That is important. So, it depends upon not only temperature difference, but it also depends basic upon the emission property of the fiber. So, we need to know what are the emission property of different fibers, and therefore, we can intelligently use fiber for developing a clothing which will protect the human body, let us say, against very cold environment. Some surfaces are good absorbers and some surfaces are good reflector also. There are some surfaces which reflect the radiative heat. So, these informations are important, because if we keep this information with us, as a designer we make use of these facts while designing the clothing for a given end use. Now comes evaporative heat transfer. Evaporative heat transfer, that is E is H E P S K minus P A. What is H E? H is evaporative heat transfer coefficient. P S K is vapor pressure at the skin surface, and P A is the ambient water vapor pressure. So, from this formula we can find out what is the evaporative heat transfer from the skin, because of the evaporation of the liquid sweat from the skin, we can find out how much heat is going to be transferred, or the insensible evaporation is continuously happening, and from that how much heat is going to be lost, we can find out using these equations. And H E can be replaced by 16.6 H C. So, what is H C? H C is the convective heat transfer coefficient. So, there is a relationship between H E and H C. So, H C values, if we know, we multiply it by 16.6 and then can use it. Now, in cold environment, large temperature gradient between skin and surrounding is sufficient to control the heat balance by convection and radiation. In a cold environmental, that is when the outside temperature is very low, the large temperature gradient will be developed, because we know skin temperature in a comfort situation will be around 34.5 or 34 degree centigrade. The surrounding depends upon the environment. If it is in the hilly region, the temperature is much lower, or if it is the winter season, the temperature would maybe 0 degree or 1 degree, 2 degree, less than 0 could be also, it can go negative. So, there is a huge temperature gradient could be there, and there could be very high rate of heat loss. This possibility could be there, and we have to arrest this heat loss, otherwise we are going to, the humans are going to suffer. Additional sweat evaporation is required at extremely high level of metabolic heat production. Generally, in cold climate, if it is, the sweat generation may not be there if we are doing normal activity, but if we are doing some high level of activity, let us say with the winter clothing, if I start doing some exercise, then there is a chance that the metabolic heat generation will rise so much that the rate of heat transfer will be much less than the rate of heat generation by the body. And if that happens, heat is going to accumulate, because I am generating at a faster rate than the rate at which I am losing the heat through the clothing. The net effect is the person will start sweating, because the thermoregulatory mechanism of the body is going to generate now sweat, hoping that the sweat is going to evaporate on the skin and will take away some heat, and by that the body is going to cool down. So, that is an automatic reaction that we have within our body. That is why we all start sweating when you do some activity and the heat balance get lost. That is, the generation of heat per unit time is much more than the rate of losing heat from the body. In that situation, this is what is going to happen. Heat of vaporization, we just need to know, that is just for information, that the energy required to change 1 gram of water into gaseous state is called heat of vaporization. So, you all know is also called latent heat. If a part of the liquid evaporates below boiling point, it extracts the necessary heat of vaporization from the remaining liquid. The cooling effect is due to this great heat loss from vaporization of the water. So, the water can vaporize, and when it vaporizing, suppose a container contains some water, and there will be continuous evaporation of water molecule from that container. So, whenever the water is changing its phase from liquid to vapor, it is taking away certain heat. From where it will take away? It will take away the heat from the water itself. Therefore, the water temperature will gradually go down, because the latent heat is taking away from the water. As a result of vaporization, the volume of a mole of water at 100 degree centigrade will change by 1700 times. So, this kind of information will be important for us, because there may be situation when the water may vaporize, and therefore, suddenly there will be a lot of volume will be required to tackle this vapor, especially when suppose we are thinking of designing firefighters clothing, where temperature outside may be very high, and if there is some water that goes inside the clothing, because of temperature being very high, that water may get converted into vapor, into steam, and there is a sudden huge change in volume. So, that will give you additional problem. 1 gram of water can be absorbed easily by the clothing, but when that it gets vaporized and there is change of volume to 1700 times, you need to think now what to do in such situations. So, that sort of possibilities could be there. So, the designer has to also take care of the worst case scenarios as well, while trying to design some product which are critical in nature. Heat loss by insensible perspiration, we have written that generally insensible perspiration is around 15 to 25 gram per hour, and if this much through this, how much heat we are going to lose? For 24 gram per hour the moisture loss, we are going to lose 16.87 watt of heat. How? 24 gram per hour means 25 by 16 to 60, so much gram per second, multiplied by 580 is the latent heat at normal temperatures, multiplied this is 4.19 you are multiplying, because this is in joule, we are multiplying by 4.19. No, sorry, this is basically you are getting in terms of calorie, and if we multiply by 4.19 we get into joule, and we get, and that is what is basically watt, joule per second is the watt. So, if we do this, the value comes 16.87 watt. That means, if the body is releasing around 25 gram per hour moisture, then at the most 17 watt of heat will be lost. The other scenario that we are generating 15 gram of moisture per hour, in that case it is going to be around 10 watt of heat. So, the insensible moisture which we are continuously generating, it is helping us to lose some amount of body heat, but it will vary between around 10 to 17 watt. Whether in a certain activity we may be generating heat to the extent of 200 watts or 150 watts or 300 watts, all depends upon the nature of the activity. So, the loss through insensible perspiration is not really very high. Heat loss by sweating. Now, when you sweat, how much heat is lost? It all depends first of all how much we sweat. Skin begins to sweat at precisely 37 degrees centigrade, and the temperature of the skin goes up. See, comfortable skin temperature is around 34, 35 in between. The moment it rises to 37 degrees centigrade, we start generating sweat. According to this gentleman Gutten and Hall, at normal rate maximum perspiration is 1.5 liter per hour, that is 1.5 kg per hour, basically assuming that the density of the sweat is close to or equal to water. So, cooling power due to the evaporation of 1.5 liter of sweat will be how much? This is generated in 1 hour. So, per second is going to be this much in terms of cc, that multiplied or in terms of gram also it will be 1500 gram, that multiplied by 580 into 4.19 will give you the total watt 1012.5 watt, that is 1.02 watt almost kilowatts of heat will be lost if we are generating sweat at this rate. So, when you generate sweat and provided that this much all the sweat is actually evaporating also, then this is the cooling power of the sweat will be. But as I said, the part of the sweat that we generate gets lost because it will drip down, and the second thing is this rolling down of the sweat and accumulation of sweat on the human body is not something, it does not give a good sensation. So, some sweat is lost, they will simply fall down or drip down, some sweat will wipe it out also because the sensation is not good. But otherwise we should know that if we are generating 1.5 liter of sweat per hour, in that is one of the extreme situation, then the cooling power of that sweat, provided the entire sweat is getting evaporated also, is 1.02 kilowatt. In tropical climate it can reach up to 3.4 liter per hour. This is also very interesting, that it is not only 1.5, it can go up to 3.4, double of 1.5. In that case, the cooling power is going to be 2.4 kilowatt. Here the assumption is that the sweat is not getting lost and the entire sweat is actually evaporating from the skin, and therefore, the body is going to get cooled, because it will take away the energy from the skin. Now, as I said earlier, the heat is also lost through respiratory mechanism. Now, because we are breathing air continuously, whether we are sleeping or not, breathing is there continuously. Now, breathing of air cools down the airways of the respiratory system and adds to the skin heat loss. This cooling increases with the lowered air temperature. So, the temperature of the outside air is lower than the body temperature, then while we are inhaling the air, a cold air is going inside the body, and therefore, it is getting warm up there, and a warm air is going to get exhaled. So, in that case it is going to cool down. The heat loss is around 15 to 20% of the total metabolic heat production. Maximum heat transfer by respiration is around 20 watt per meter square. This has been shown by some people, and in warm and humid air it is around 10 watt per meter square. Through respiratory mechanism that we have, that when you are breathing air, through that also some heat transfer is happening. The loss can be reduced by simply cover of the mouth and nose. So, this heat loss which is there, if we are in a cold climate, then we need to, if we want to reduce this heat loss, then we can cover our nose with a simple cloth and we will feel warm. So, many of us will find that when you are moving in winter and we are outside the home, we try to cover the nose and the mouth by a muffler, or if you have a shawl, with a shawl also. So, this is going to reduce the heat loss and it will keep you little warm. Compared to 20 degree centigrade, heat loss approximately doubles at 5 degree centigrade. This is what you have to remember, that when the outside temperature is 20 degree centigrade, whatever heats I am losing, it will double at 5 degree centigrade if the temperature goes down to 5 degree, and increases to 3 times at minus 10 degree centigrade and 4 times at minus 25 degree centigrade. So, if we calculate that how much heat we are going to lose at 20 degree centigrade, then we can extrapolate that to find out how much we are going to lose when the temperature is falling from 20 to 5 to minus 10 and minus 10 to minus 25. So, as the temperature keeps falling, the heat loss is going to increase, and therefore, if we know the situation, how much fall of temperature is possible, then we can think of designing a clothing which will protect a person in such kind of environment. Because the informations are important to know from the point of view of the requirement that we may need while trying to design cold weather clothing. Now we give you an example, such simple calculation. Let us say a naked person is sitting in an open field. Okay, the skin temperature, let us say 30 degrees, 37 degrees centigrade. It is the skin temperature we are assuming. We know that 30 degree centigrade is the core body temperature and skin temperature is usually 34 degree. Let us say it is 37 degree centigrade, and a naked person is sitting in an open field. The ambient temperature is 45 degree centigrade. That means, it is a very hot climate. The air is still, so there is no air movement. The metabolic heat production is 90 watt, because he is not doing any activity, but simply sitting idle. The insensible perspiration generation is 25 gram per hour. That is the insensible perspiration he is going to generate. Assuming no convection loss, calculate total heat gained by the person. Okay. How much is the total heat the person is going to gain? That is what we need to calculate from this data that has been given. So, this is basically the total heat. Solution is, there are two sources of heat transfer. One is by conduction and by radiation. Why convection is not there? Because air is still. So, there is no convective heat loss. And there is a single source of heat generation, that is metabolic heat generation, because the body is generating 90 watt of heat. So, that much heat is generating, and now the body is going to receive some heat from outside, because the outside temperature is 45 degree centigrade. And now, there are two different modes through which the body is going to receive heat. One is conduction, the other one is radiation. All right. So, this data that has been given is stated in this particular table also, is being shown here. Skin temperature is 37 degree centigrade, ambient temperature is 45. So, temperature difference is how much? 8 degree. Conduction heat, how much we are going to gain? We do not know, question mark. Convection heat, how much we are going to gain? We are saying there is no convective heat gain, it is 0. Radiative heat gain we need to calculate, it is there is a question mark. Perspiration we have said 25 grams, so we have to calculate also how much heat we are going to lose if we are taking into account the insensible perspiration generation. So, we can also find it out. Basal heat production is 90 watt, and we need to calculate now how much heat the person is going to gain. So, standard body surface area is usually 2 meter square. It has not been given in that example, but usually it may vary from person to person. You may say a person's there are people of different size, different height. So, therefore, the skin surface area may vary from person to person. It obviously varies. A standard is taken, and that is around 2 meter square. Emissivity has been assumed to be 0.97 of the skin. So, rate of absorption of heat due to radiation from the surrounding can be found out from these equations. P n equal to epsilon sigma T to the power 4 environmental temperature and T skin to the power 4, both are in Kelvin. So, this is what we have already stated earlier. From there, if we what is the environmental temperature? 45. So, 45 plus 273, that will give you temperature in Kelvin. Body temperature 37 plus 273, that is giving in Kelvin 310. Now, you use this formula, put these values to find out what is the absorption of heat through radiation, and if we just simply substitute these values in this equation, we get a figure 54.5 watt per meter square. So, for the whole body it is going to be this multiplied by 2, because 2 meter square is the surface area of the body. So, just simply multiplied by 2, that is 109 watt is the heat that the body is going to receive through radiation mode from the surrounding air. So, air is actually the source of heat now, and from the air heat is moving towards the human body. The next is heat of absorption through conduction. If we try to find out, because the air is in contact with the human body. So, how much heat is going to be transferred from the air to the body through conduction mode of transfer. Now, this equation is the basic heat transfer equation for conduction. Q by T equal to K A T of the environment and temperature T of the skin divided by D. A is the area of the human body, K is the thermal conductivity, D is the thickness of the air layer. Now, effective distance of ambient temperature air is considered around 5 centimeter, or that is equal to 0.05 meter. The skin area, standard skin area is considered always 2 meter square. Skin temperature and air temperature have been given. So, air temperature is environmental temperature. From there, if we again substitute these values, we get in this equation, we will get this figure 7.68 watt. That is, through conduction, the amount of heat that the body is going to absorb or body is going to receive is only 7.6 watt, 68 watt. So, how much we are receiving from radiation? That figure was 109, and we are receiving through conduction is only 7.68, or let us say 7.7, make it 8 also. So, that is only around 8. Now, therefore, the net input to the body is 109 watt through radiation, 8 watt through conduction. Basal heat production, because the body metabolism is 90 watt. So, total heat gain is going to be sum of these three, that is 207 watt. That is what is going to be the heat gain. Now, if the person has to feel comfortable, the person has to generate sweat and the sweat has to evaporate and cool down the body. So, how much sweat evaporation is required to cool the body? As in this case, if I want to make the person feel cool, so whatever heat he is generating, the same heat has to be lost through sweating mechanism if he is going to lose the heat. Now, heat loss due to evaporation of 1 gram of sweat is how much? Is 2430 1 into 580 into 4.19 as a 2430 watt or 2.4 kilowatt. Hence, required perspiration rate for dissipating 270 watt is going to be how much? 207 by 2430. So, it is going to be 0.0851 gram per second, that means 5.1 gram per minute, 306 gram per hour or 7.34 kg per day. So much sweat the person has to generate per second. It is only 0.0851. If I convert into minute, it becomes 5.1, convert into hour 306 gram per hour, and if it is per day 7.34 kg per day, and this value is much more than the human capability to generate sweat. Per day, how much we have seen earlier is around 3.4 kg maximum. Obviously, so much of sweat a person cannot generate, and hence the body will not get completely cooled through sweat generation, not possible. So, if we keep the person there in that environment for a long time, the person is going to die finally. So, he may bear the heat for some time, then he has to move out to some other place, so that the heat that he is receiving per unit time, that reduces. With this, I think moisture release due to insensible perspiration, as we said earlier, 25 gram per hour, and we know for that also some. So, that is so much 306 is the sweat, and this much maybe through the insensible perspirations, but as I said, even then so much sweat cannot be generated by the person, and therefore, it is very difficult to keep the body cool if it is there for a long time. So, with this we close this particular topic, that is heat exchange between human body and the surroundings. The surrounding in this case we have considered to be an air. Okay. With this, let us close today's session. Thank you.